is a joint work with Professors Victor, Carlos Núñez, and Julian Salas. I'm an associate professor at Open University of Catalonia. And yeah, this presentation is about security, trust, and privacy in 6G networks. Let's first introduce which are the novelties of 6G. 6G networks will introduce new frequency bands at higher frequencies. This will give us faster speed transmissions, low delay, and more reliable and stable connections. With these faster speed connections and everything, we can introduce new applications, which are mainly based on real time. We will have applications like virtual reality, we will have teleportation, we will have smart cities, and we will combine all these applications with a lot of sensors and devices of IoT. And this IoT will bring us new data that is spread all over around the world. And with this new data, we can generate new intelligence. IoT will bring us, as I said, a lot of new information, and we can provide services, for example, in the smart cities like traffic management or energy usage in real time. And this is very important, that we will use real-time applications, and so we will use the faster speed of the networks also to produce applications that has to respond very fast to the needs of the society. For this, we will also introduce a part of the IoT technologies. We will introduce in 6G networks the technology of artificial intelligence. Why? Because artificial intelligence can improve us a lot this reaction of the network, this real time. We will use artificial intelligence in different parts of the network, from the radio access to the decisions that has to be taken in all the network, because we want that these decisions are fast, are appropriate, and are in real time. So artificial intelligence will be very important to 6G networks to decide how the management of the network has to be produced. This presentation will go first on general introduction of mobile network architectures. Then we will focus on artificial intelligence technologies, specifically for 6G networks, why we will use AI. And then we will review the security, trust, and privacy challenges and attacks in AI-driven 6G networks. So we will focus on 6G networks, but specifically on the problems associated to artificial intelligence. And finally, we will give some conclusions of this work. First, I will introduce mobile networks in general. The different generation of mobile networks has been composed of three parts. One part is the RAN, the radio access network. This is the part where users connect with their devices, tablets, mobiles, laptops, or even IoT devices to the network with the radio access. This RAN network is composed of the user equipment and also to the radio nodes, the antenna, and also the routers, the switches, everything involved in managing this radio part of the network. Then we have a transport network that connects the radio access, the RAN network, to the core. All the traffic of the network has to go through this transport layer, through this transport network. And finally, we will have the core network. The core network is like the brain of the network, where all the decisions, all the management of the network, user access, resource management, interconnection with other networks like internet or other services, other aspects is realized. So we have the radio part, transport part, and then finally the engine or the brain of the network. In 6G networks, some changes are introduced. First, the core network will be more softwareized with software-defined networking. The services, the different aspects of the network will be produced in containers and more softwareized. This will give us some properties, like we can set up different services in real time and more easily. And we can adapt the necessities and requirements of the network to the real-time aspects that we need. We will also use network function virtualization. So the functions of the network, for example, user access, security controls, etc. It's not in a hardware-based solutions, but also in software-based and virtualized, so that, as we said before, we can set up these different points of access in the network in a distributed way, more easily and more flexible to set up and set down some of the functions. Then in the radio access network, in the radio part, we will also separate the different functions of the RAN network in different components. And these different components will also be virtualized and with open interfaces. It's important that we will have open interfaces here, because what we want here is to have different providers and different vendors. So the RAN part of the network, it's no longer a provider that gives us all the services. We connect to a telco operator, and this telco operator has the antennas, has the switches, has everything. But this will be like very small parts of the functions of the radio access. Every company, every provider will be specialized in one function of the network, and then they will interact all together to create the radio access part. This is quite interesting because we have more flexibility, and vendors can focus on one specific properties of the network, but also has some security problems, as we will see then. Another innovation of 6G networks is that the radio access part, the transport part, and the core part of the network will work more jointly together, will be more mixed. And the core part of the network will not be longer in a coordinated server, in a centralized server in the internet, for example, but it will be more engaged to the users, and we will use fog edge cloud architecture to deploy this kind of services. This will set up this MEC part of the network, which is multi-access edge computing, in which there will be functions of the core network and also of the RAN network that will be much close to the users. This has some implications. The network can be much fast in this way, because data doesn't have to go through the core network to take solutions, but we can have just feedback in a much more efficient way in the MEC part, in the fog layer, or in the edge part of the network. We can have response of the network, and also has security implications, because the data doesn't have to travel so far away, and doesn't have to be processed or inspected by so much networks, but it's much more near to the user. So it has some security prevention attacks. No, the data is more close to the user, everything is more fast, everything is more efficient. So this kind of architecture has a lot of benefits: flexibility, fast, less delays, more security and privacy, but we also have some drawbacks, as we will see. In this kind of networks, we need to introduce artificial AI solutions to be able to manage all this massive quantity of data more efficiently. In the first part, we will use AI in the frequency technologies in the lower part of the network. When devices are connected to the radio access, we will need to put some intelligence here in the radio, in the adaptive radio access, so that we can avoid multi-hop problems. We can avoid if there are interferences with other terminals in the radio, so that the transmission of the radio is better and more fast. So for one part, we will have these AI technologies in the radio, in the radio parts, in the adaptive radio. Then we will also put AI in the end-to-end communication from the device to the receptor of the radio. We will need to optimize the the source and the destination of the radio in a jointly based. This was very difficult to do with nowadays technologies, with rule-based technologies, because optimizing the two elements at the same time, it was very costly. They are in different places, in different environments, and trying to optimize the two things was complex. Now, with AI technologies, it's more feasible. We can try to optimize based on testing and reproducing what is best for each loop of the network. So we have different trainings of this solution, and in each step, this train gets us a better solution, and we can optimize the two parts of the network at the same time. Then we will put AI in the research management so that different radio links, different channels, different frequencies can be set up in a flexible way and also in an autonomous way. When a network sees that it needs more resources, because we have a lot of clients in that network and we need to set up more frequencies in that antenna, we can set up new channels, new frequencies in a real-time based basis, and also in an autonomous way. So we tend to create autonomous networks that can be self-managed. Then we will also use artificial intelligence to predict the user behavior and also environmental conditions, so that if we know, I don't know, at 5 o'clock in the afternoon, a lot of people is connected from this place, I will put more resources in, I don't know, in the park or in the streets or in whatever places. If at 10 a.m. in the morning, people is more connected in the companies, I will put more effort in that kind of connection. So we can predict where will be the transport and where we need more resources. And also for the user, we can predict if, for example, a user has, I don't know, bad skills or bad behaviors, and he is reproducing risky actions, so that he can get a security attack, or he can uses a lot of the network in a time base. So I can give more attention to some kind of users and predict what he will do in some time of the day and put more resources in that users. And finally, we have also the detection of cyber attacks. We will put also artificial intelligence in cyber attacks, because it is very easy to detect cyber attacks when we know which attack will be produced in the network, when we know the rule-based attacks are very easy to detect, but it's not so easy to detect unknown attacks, zero-day attacks. With artificial intelligence technologies, we can put intelligence on the defense methodologies and try to detect and block attacks in a more efficient way. So with all this landscape and this environment of the CG networks, now we will try to introduce which are the security challenges, the privacy challenges, and the trust challenges in this kind of networks. We start with the security challenges. As we said, we have a network with a lot of devices, with massive interconnections of the users and the devices. And one of the first challenges we encounter here is the physical tampering, because we have small devices, small IoT devices spread also in public places, because we want to take information of a smart city, for example. Physical tamper, it's more risky, it's more challenging. We can have people trying to compromise devices in the street. And if this device is compromised, the data integrity, it's a problem. We can have a cascading effect on all the network, because if the data is not good, then the solutions based on this data will not be good. Also, we have a challenge in the operating system and protocol heterogeneity, because we have different devices and we don't have only one operating system in these devices, but a lot of protocols, a lot of operating systems. And we have a lack of standardization nowadays on which are the things that we have to use in this kind of networks. We have some problems of security, because sometimes it's difficult to interconnect these different operating systems, devices, and at the end, they are integrated with the low basic levels of everything, of security, of privacy, etc. Another problem of these networks is the user interfaces, because in small devices, in lightweight devices, IoT devices, we usually don't have user interfaces. We don't have screens, we don't have keyboards, we don't have anything to talk with the devices. So when there is a threat, when there is a problem, or when there is an update, a security update to make in the device, it's difficult to make this update, or difficult to see if this device alerts of some problem, because there is no this interface. So this is also a challenge. Another challenge is that we have moved the computation of the network from the cloud or from the centralized server. We have moved this from the centralized servers to a near place of the user, to an edge device, a fog device. But these fog devices, edge devices, are more lightweight, and so doesn't have the computational power to analyze and to track all the security defenses that a core network can have. So we lack some robustness when we put things in the edge. Also, security protocols that are very robust in internet networks or protocols are not so good for this kind of networks that are so distributed, that include very different heterogeneous devices, and which need real-time solutions. So also security protocols are a problem here, because not all of them are adapted for this network. Another problem is this edge containerization thing. We virtualize all the devices, but this virtualization is usually not made using virtual machines that are it's a very strong sandbox, but we will use containers because are more flexible, more lightweight, etc. Containers are not so isolated hosts. So here we can have some security challenges of what happens if the host is compromised. If we have a host compromised, this compromised can also affect the virtual functions that we have in this network. Or if a virtual function is compromised, can this affect to the physical host, and so pass this problem to other virtualized functions? This is also a challenge that we encounter in this network. This is very related with SDN constraints, with software-defined network constraints. We have tried to decouple, to separate the control plane to the data plane of the network, but then if we separate so much this control plane to the data plane, we can have vulnerabilities on one plane, DOS attacks, etc., and the other plane is not aware of that, and it's not able to manage all the information of the users, or not be aware of the attack. Another problem is the complex security enforcement. We have a lot of mobility, different domains, because we have different providers, different vendors mixed together to give a unique solution to the user. But in fact, we have different domains, different security domains, and having a policy and a security enforcement that it's easy to manage for all these devices and users that are connecting at the same time through these different domains, it's very complex. Also, we have the problem of open interfaces. We have said, well, because we have different vendors, we have different providers, we need to have open interfaces so that people or technologies can talk one with the others. But if we have open interfaces, for example, in the radio access part, we will open the door to different attacks, because nowadays in all networks, radio access is very limited, and only the telco providers have access to these radio access links. Now, if you open the door to open interfaces, every user, every malicious people can have access to the radio links. So this gives us more attack surface and problems. Finally, multi-vendor interoperability. If we have multiple vendors, we can have inconsistencies in the security implementations, and so patch management and everything, and this can give also some security problems. And then we have also the problems of powerful attacks. Not only the good part of the network will have artificial intelligence and make improvements on the networks, and will provide more efficient network services, but also the attackers have access to this kind of powerful computers and powerful engines, and they will also use artificial intelligence and powerful devices. So attacks are every day more powerful. So this is also a challenge. With all these challenges, we will have different attacks in the networks. We'll divide the attacks on the 6G networks in two parts: poisoning attacks and evasion attacks. Poisoning attacks are the attacks that are related to trying to attack the training of the network. Now we are focusing only, we are focusing only on AI systems. Security attacks for the artificial intelligence solutions of the network. So when we try to modify how the network is learning, we have poisoning attacks, and these attacks are divided in three parts. In data poisoning, when we try to attack the data set or the data, the online learning of the system. For example, we change the labels of a data set, we hide some data from the data set, we introduce new information in the data set. All these are data set learning attacks. And these are due to, as we said before, containers are not so isolated, the complex security solutions. We can have physical tampering in the devices that give us this information, etc. So we have different attacks here due to data poisoning. How we will solve this? We will solve this with encryption, better encryption, with anomaly detection of these attacks, with strong authentication, with zero trust architectures, with intrusion detection. We have different solutions here, but the problem is that these solutions are quite hard to implement, are not so lightweight. So we need to provide more lightweight solutions, more real-time solutions for this kind of training, because this is a very important part for 6G networks. Another kind of attacks in the 6G networks, in the learning part of 6G networks, is the algorithm poisoning. If we try to modify the algorithm of machine learning or in general artificial intelligence learning. For this, we can have backdoor attacks or DOS attacks. For example, if we have federated learning here, that we don't all, it's quite a quite well solution in 6G networks that are very distributed. They don't have only an artificial centralized solution for artificial intelligence, but a federated solution. When we have these federated solutions in which different nodes in the network are collecting data and are creating a solution for the artificial intelligence altogether. When the weights of the systems are created, we can have DOS attacks here in such a way the data, the feedback of each separated device, of the devices that come from this federated learning, are not set up in the system. So the system then, it's the model of the system, it's corrupted. It's not learning in an efficient way anymore. The algorithms is corrupted. And we can have solutions here like blockchain, in which we can have track of all the systems involved in the learning of the network, so that we can have knowledge if all of them are participating, if all of them are contributing in the network in an efficient way. But of course, this is also challenging to implement these kind of solutions. Also, intrusion detection can be a solution to know if someone is providing intrusions on these different nodes of distributed elements in the network. And another kind of attack in poisoning model on training models, it's a model poisoning. Also, data poisoning and algorithm poisoning at the end are model poisoning, because we are modifying the model of the network. But we also have some specific model poisoning in which we have black box adversarial attacks that modify the logic of the model. If I have a root-based attack in the network, and we can modify the solution of the centralized part of the network and change the weights of the network and change the logic of the model, I will have here also a powerful attack. To solve this, we can have anomaly detection, but this is also very challenging because artificial intelligence has the problem of not being transparent and have the explainability problems. So when we have a solution of artificial intelligence, we really don't know if this solution is good or not. We have to trust in the model. We have to trust that the model is behaving as it should to behave, but we don't have a proof. So we have problems here. We have a challenging part here because if the model is poisoned, if corrupted, we don't have much proofs, much evidences to know if it really has been poisoned. So this is a challenging aspect of CG networks and AI systems. For now, I have been explaining the poisoning attacks, which are the attacks that affect training of the network. And then we have the evasion attacks. These attacks affect the execution of the network. Excuse me. These kind of attacks, mainly misclassification adversarial attacks, in which excuse me, in which an attacker knows very well the model of the network and it's able to create an attack that is misclassified by the model, because you know exactly how the model is over trained or no, which are the levels and the weights of the model. I can make some attacks that achieve a misclassification. For this, it's important that we use a very diverse data sets, and that we can have a very extensive validation of the model with robust data, with very diverse data sets with anomaly detection. Until here, we have talked about security challenges and attacks of CG networks. Now we move to the trust parts of the network. They are very related to security because if we detect security attacks in a network, then the trust is also mistaken. We cannot trust in a system that gets bad results or that has bad security. But let's a closer look at trust. Which are the challenges of trust? The first challenge is the extreme massive connectivity. We have a lot of devices connected in CG networks, a lot of IoT devices, a lot of connections of every user, a lot of devices per user. So this connectivity demands requiring collaboration of a lot of people to define and to select which devices are trustful and which ones are not. And this is complex. Another problem is training misleading. The reliance on AI model, as we said before, it's risky because AI models are not explainable, are not transparent, and reliance on AI models it's also a problem. Another problem is the data and infrastructure integrity. We can have compromised software trust change. So if we have a problem in one part of our chain, of our software chain, we have a lot of components that give us a trust model. If one part of this model comes from a software vendor, from a provider that has a security hole in their software, this security hole it's also spread in our solution. So this software chain, it's also a problem for the trust model. Also, we have the problem of trust quantification, how we quantify trust. Defining unified terms to quantify and evaluate trust among different partners is a challenging. Also, trust expansion is a problem because we have different users in very different geographical areas, requirement needs, software needs, hardware needs. So how we can expand trust to all the devices which are very heterogeneous. And also we have the problem of emerging technologies. We can try to solve these problems of trust, of track the users, track how they are behaving and everything with, for example, blockchain or DLT technologies. But these emerging technologies are new technologies, and so they face new emerging security problems or trust problems. For example, DLT faces governments and regulatory uncertainties. So trying to provide solutions based on these new technologies also provides new challenges. We have different attacks related to these challenges. They are quite similar to security attacks. The first two ones, for example, poisoning attack, evasion attack, are the same ones as in security parts, because if we have a problem of security in these networks, if the system is not able to separate good behavior to bad behavior, we have a trust problem. The reliance of the network, it's not good anymore. Also, we have a problem of model extraction. If we are able to extract some weights of the model or some, we can infer some properties of the model, we have also a trust problem because we do not trust the infrastructure anymore. We have also identity spoofing problems. If we have a user that can spread the identity in different fake users, the trust of the system is hindered because he can try to attack his own trust, making good reviews of his users in a malicious way. Also, insider attacks are a problem, and repudiation attacks. Repudiation attacks is when you make a good action, for example, for the network, but some people, some devices say that you have done a bad thing. How we control that this repudiation of the actions of the network are good or not? How we can trust the people that is saying that the network is behaving good or bad? This is also a challenging task to do. And also we have reentrancy problems. These are more related to emerging technologies like blockchains and code scripting. We can have problems in these scripting attacks, and we don't know which is really the malicious boy in there, which are the good ones and which are the bad guys in code auditing. So we have different problems here that can be tried to be solved with zero trust models, with adversarial examples, noise injection. But these kind of solutions, and we can have theoretical, we can have some strategies to solve this, are not really nowadays implemented in this kind of networks that need to be executed and deployed in real time. So the strategies, the solutions are there, the theoretical solutions are there, but trying to translate this in a real-time network that has to move in less than 10 milliseconds, solutions in less than 10 milliseconds, it's really challenging, and this is a threat. Finally, the privacy challenges that we have in these networks are that, well, we can try to review it here. We have complex identity management, how we put identities in all these Internet of Everything devices. We have devices everywhere. How we can identify in a clear and indissoluble way that a device, it's what it really says to be. How we authenticate and authorize these devices when we have a lot of devices and each user has a lot of things. Another problem is eavesdroppers. Nowadays, with radio access, it's difficult to have eavesdroppers because 4G technologies, 5G technologies are quite isolated for radio telcos, and only radio telcos are able to access these devices. But now we will have open interfaces, even in the radio access and in the core networks. So we will have much more eavesdroppers that will be able to listen to the connections and extract data information from that connections. Also, we will have the problem that the network will use user-generated data to extract information and models of the network. We will have, I don't know, for example, in IoT systems, we will have these IoT devices that will generate information for the system. But this information has sensible information because this information gets data from the environment, and this environment is connected with people and with the actions of the people. Which kind of devices were surrounding an area, which kind of people is connecting at a given time, which kind of devices or applications has more traffic. So this user-generated data is used for modeling these CG models, and this is risky for the privacy. And also we have the problem of net containerization, because as we have said before, all the devices are not longer physical devices, but we have virtualized devices and containerized devices. This is more challenging because these containers are not so much isolated. We have a lot of problems here. And perhaps the list it's too much to go one by one. We can have deception attacks here, side channel attacks, because we have an attack in one channel, but from the other channel we can have some clues of what's happening on the other channel. We have information disclosure attacks, location tracking, because we can know with a GPS where the users are located or whether data are located. We have data leakage, eavesdropping, file injection, model inversion, membership inference attack, property inference attack. We can control this with differential privacy, noise addition. We have different solutions in which we try to put like fake data in the data sources to make this valuable data so masqueraded between this fake data. So it's not so easy to detect which is the fake data and which is the real data. But it's not so clear how to prevent this privacy attack, because we have so much information that inference attacks are always there. And finally, to conclude, we will say that CG networks will increase connectivity, cloudification, and IoT, and this will expand the threat surface. And with this expanded threat surface, the problems of security, trust, and privacy will increase. Attacks on artificial intelligence are highly dangerous because of the complexity solutions of transparency and explainability of artificial intelligence. And also AI facilitates more advanced solutions of power for attacks. So everything is more powerful and attacks are also more powerful. So this is all of my presentation. Thank you.